And the next speaker is Jennifer Schober, who will tell us about primordial magnetic fields and their amplification. So please go ahead.
Thank you very much. How do I change slides here? Okay. Okay, so it's great to be here in Heidelberg. Actually, most of the results I show today have been produced here in Heidelberg. And I will talk about magnetic fields in primordial star formation. So let me start with a short overview. So we know the precise initial conditions of primordial star formation from lambda CDM cosmology. So we know that the first stars form in these primordial mini halos, and these collapse due to molecular hydrogen cooling at redshifts between 20 and 30. So I like to add two more points. So first, there's turbulence. Turbulence can be driven via virialization or via accretion, and there are weak magnetic seed fields. So these are typically much less than 10 to the minus 10 Gauss, orders of magnitude below that. For comparison, the Milky Way has a magnetic field strength of 10 to the minus 5 Gauss. These fields, they are created during inflation or during phase transitions in the very early universe, or by plasma effects like the Biermann battery or other plasma fluctuations. As they are very weak, they have not been considered for a long time in primordial star formation. But the combination with turbulence makes small-scale dynamo action possible. And this process can amplify magnetic fields by converting turbulent kinetic energy into magnetic energy. So for understanding this process, we need to understand turbulence. And this is a short illustration of turbulence. I show here the power spectrum, so energy as a function of wave number. At large spatial scales, so at small wave numbers, we drive turbulence. And in the classical Kolmogorov picture, we have these turbulent eddies on large scales initially that decay into smaller and smaller eddies. And by this, they transport the kinetic energy to smaller and smaller spatial scales. We call this the turbulent cascade. And the range we cover here is the inertial range. This process comes to an end when we reach very small spatial scales. Below the viscous scale, energy is dissipated and basically goes into heat. The shape of the spectrum, it's here a power law, and the exponent of the power law depends on the type of turbulence. At the same time, the velocity, of course, depends on the length scale on which we are, and the scaling here is called theta, and this theta is in classical Kolmogorov turbulence 1/3, but it can reach values up to 1/2 for highly compressible Burgers type turbulence. In astrophysics, we are often in the situation where we have to deal with compressive turbulence as we have very high Mach numbers. The typical Reynolds number in this problem is, which is defined as the ratio of velocity times length scale over viscosity, is of the order of 10 to the 7, so we are highly turbulent. The physical length scales included are the following. So forcing takes place on roughly the Jeans scale, which is 100 parsec. And the viscous scale where energy dissipates is much below a parsec, so roughly 1% depending on the type of turbulence we have. It's given here by the Reynolds number, and the Reynolds number basically gives us the size of this inertial range. So we have a huge scale separation. So how does turbulence now amplify magnetic fields? This is illustrated here. I show here a closed magnetic flux rope, and it has a cross-section A1 here, and a field strength B1. B times A is the magnetic flux. This is a conserved quantity. So if turbulent motions, for example, stretch this flux rope, you see that the cross-section decreases, and this means that the magnetic field needs to increase in this step. You also see that the field lines are closer together now. Then we can twist this flux rope, fold it, and merge it again, and we end up with a flux rope that looks the same but has an increased magnetic field. And then we can start it all over, and in the end we have an exponential growth of magnetic energy. The growth rate is proportional to the inverse eddy time scale. So it's because these turbulent eddies are responsible for stretching, twisting, and folding. And this is a quantity that depends on the spatial scale, because the velocity and the time scales depend on the scale. And the time scales are shortest on the smallest scales of our problem. And this is the viscous scale. And this is why it's called the small-scale dynamo. So we describe this with MHD. And this here is the induction equation describing the evolution of the magnetic field. It consists of an advection term, which includes here the velocity that can amplify the magnetic field, and it has a dissipation term that can dissipate the field again. Now, what we do is we separate now the fields into mean fields and fluctuating fields like this, because we are only interested in the fluctuating part. These parts evolve much faster because evolution takes place on smaller spatial scales. The mean fields, they have time scales that are related to the forcing scale or to the large scales of the system. So what we do is we employ correlation functions to model the turbulence, and we use this spectral scaling of the turbulent fluctuations. And this has been described in these articles here. So basically, we put this in the induction equation and solve it. And what we find is this solution for the growth rate. So the growth rate depends on the Reynolds number. For larger Reynolds numbers, we have a smaller viscous scale, so the small-scale dynamo is more efficient. And I've put here the solutions for incompressible turbulence and compressible turbulence. The scaling is less for the compressive case. Okay, so now how does this look in the spectrum? So again, I show here the energy as a function of wave number. And I have here the turbulent spectrum. And the magnetic field grows initially on very small spatial scales. It actually peaks on the resistive scale, which is the scale below which magnetic energy is dissipated. Now, initially, the field just grows exponentially on that scale. And at some point, it becomes very strong. And then we need to include back reactions from the magnetic field onto the velocity field via the Lorentz force. We are entering the nonlinear phase, and it becomes more complicated because now we don't only have to solve the induction equation, but also consider the evolution of the velocity field, which is governed by the Navier-Stokes equation. It can be done under some approximations analytically. For example, Chikoshi-Hien has modeled this with the assumption that in the nonlinear phase, the peak of the magnetic spectrum moves to larger spatial scales at the local eddy time scale. And Dominik Schleicher has generalized this for different types of turbulence. And he finds that the magnetic field in the nonlinear phase does not grow exponentially in time anymore, but as a power law. And again, we have here dependence of this power law index on the type of turbulence. So in the nonlinear phase, as you see here, the magnetic field shifts to larger spatial scales. And at some point, we reach saturation. I call this K star here, the scale, and the dynamo amplification comes to an end. Now, we were interested in this scale, so which scale can we reach with this small-scale dynamo, and of course, in the final magnetic energy that we can gain from this process. So what we found at some point was this old paper by Subramanian. He suggests that if the magnetic field is strong, the magnetic resistivity becomes an effective resistivity that depends here on the molecular one, plus some term that depends on the magnetic energy. And this term includes a time scale that he calls response time. Now, what we did is we model this response time scale as the turbulent eddy time scale. So we made it scale dependent via our turbulence spectrum, and we find this expression. So what we did with this effective resistivity is we put it into the induction equation, and we looked at here the dissipation part of the induction equation to estimate the dissipation rate. And we find this expression for the dissipation rate that now is a function of this effective resistivity, which again depends on the magnetic energy. And now we used this dissipation rate and we compared it to the growth rate of the dynamo. And we say that amplification on a scale k ends as soon as the growth rate equals the dissipation rate on this scale. Saturation of the whole dynamo process occurs then when this relation holds on all scales above scale k star. And this k star is determined by the critical magnetic Reynolds number, which also is responsible for the onset of dynamo action. And then we looked at the spectra, the saturation spectra, and integrated them to gain the saturation level, which is like the magnetic energy over the kinetic energy. So we've calculated that for different types of turbulence and different situations and compared it to numerical simulations. So you see here this saturation level as a function of the Mach number. So these are simulations by Christoph Federath, and the purple crosses show solenoidal forcing, while the gray crosses show compressive forcing. If we are in a regime of low Mach numbers and we have solenoidal forcing, we are simulating Kolmogorov-like turbulence, incompressible turbulence. And for this, we just look at our theoretical model and calculate the saturation value, and we find something within this blue band here, which is of the order of 40%. We can compare it also to other simulations and find nice agreement. For high Mach numbers we are studying compressive turbulence, and there we find a value of less than 1%, which is also in agreement with simulations. Now, it's interesting to look into a primordial halo, and we've did this in 2012 by using a chemistry code from Clover and Savine to calculate the density, evolution, temperature, and ionization degrees. And we calculated from this the viscosity and resistivity to get the Reynolds numbers and to calculate the growth rate. And then we follow the magnetic field evolution, which is governed by this equation. We have amplification via the dynamo. We have spherical compression that takes place when we just let our halo collapse and have flux freezing. And we include dissipation by ohmic effects and also by amplipolar diffusion. This is the result. So this is the magnetic field as a function of density now. We first have this kinematic phase where we start with a very weak magnetic field, 10 to the minus 25 Gauss, and you see that we can overcome more than 10 orders of magnitude on a very short time scale here. Then we enter the nonlinear phase where the magnetic energy is shifted towards larger spatial scales, and at some point we reach dynamo saturation. From there on we still have spherical compression during the collapse, which is much slower than the dynamo, of course. So we reach saturation here of the dynamo when we have a density increase of a factor of 4 only. So we are like on the freefall time scale here. And the field we get here is 10 to the minus 6 Gauss, which is already comparable to what we have in the Milky Way today. Okay, so I've shown you that we can get very strong magnetic fields with this dynamo, and now we have to deal with all the consequences for primordial star formation. We need to add an additional magnetic pressure. We have effects that transport angular momentum, like magnetic braking, jets and outflows. And we have additional physics going on in protostellar disks, like magnetorotational instability, for example. Now the big question is, what is the net effect of these magnetic fields on the mass and multiplicity of the first generation of stars? And I think there are a lot of open questions. There are first simulations by Machida and Doi, but I guess there's a lot of more work to be done. And to conclude, I've shown you that the turbulent dynamo can amplify magnetic fields very efficiently with high growth rates. Saturation occurs when roughly something between 1 and 40% of the kinetic energy is converted into magnetic energy. And in primordial mini-halos, this takes place on roughly the freefall time. And the effects of these fields need to be studied in future simulations. And I thank you very much for your attention.
Thanks for this very nice overview of magnetic field amplification and magnetic field effects in the primordial universe. The podium is open for questions.
So I would like to ask you about the dissipation process. So you said you included both the ohmic and ambipolar diffusion. So actually, which was more important in which region of density?
So ambipolar diffusion is more important, especially since the magnetic field becomes very strong.
So in whole the density range in your calculations, actually the ambipolar diffusion is dominant?
It becomes more and more dominant when the density increases, of course. But for most of the time that I show here, it's the dominant effect.
Okay. Yes.
So next question by Ralf Putritz.
Jennifer, what scale did you reach as you're growing with the turbulent dynamo? What physical scale do you reach as the largest significant length scale for your magnetic field, say compared to the initial Jeans mass?
Yes.
Length.
Length scale you are talking about, right? Yeah. So that depends very much on the type of turbulence and on the magnetic Prandtl number also. So it's for low magnetic Prandtl numbers, we reach something like a half of the forcing scale, which would be 50 parsecs. For very high Prandtl numbers, this can be much below. It can be of the order of a parsec only, the peak scale of the magnetic field at saturation.
You showed a figure with Mach number on the x-axis, and you were plotting the fraction of the kinetic energy where you get saturation.
Yes, so magnetic energy over kinetic energy.
Okay. So my question is, even in supersonic turbulence, the turbulence is sonic or even subsonic on the smallest scales. So what is that Mach number? Is that the Mach number of the largest scales, or is that the local Mach number?
So in the simulations, I'm not very sure about the simulations here, how this Mach number is defined. Can you?
So I can say something about it. So it is the overall RMS velocity dispersion divided by the sound speed. So most of the energy is indeed carried by the large-scale modes.
Yes, okay. So in your analysis of saturation, do you take into account the fact that the local Mach number is dropping as you go to smaller scales?
No, we just model the turbulence spectrum, and we vary the slope of the turbulence spectrum for compressive turbulence. We don't have any breaks in the power law included in our model, so we don't have a direct Mach number dependence in our model. We just vary the overall slope of the spectrum.
Thank you.
So I see no more questions, so let us thank Jennifer again. And what